Hi there, this is Matt Heffernan. Welcome back to my channel. This is number 20 in the Slidey Vlogs series. So we've been doing these vlogs for a while, and I'm getting back to one of my sort of sub-series within Slidey Vlogs, of course, the 8-bit Battle Royale. And I've gone through a bunch of different 8-bit computers, but I think a lot of people are under the sort of impression that a game console is somehow like something other than a computer. And today I'm going to show that indeed a Nintendo Entertainment System, the most popular video game system of the 80s that at least brought the North American market back from the brink of the video game crash of the early 80s, and how it can actually be used for generating a Mandelbrot set. It can just do some hardcore math. First, let's go a little back and see what the Royal Rumble, sorry, the Battle Royale has produced so far. Now, the top five computers that I've looked at are all now have assembly language versions, and they're all either 6502 based or Z80 based. And the Commander X16, not surprisingly, leads the pack, but it's not really fair as that's a modern 8-bit system and it is running a 65CO2 at 8 megahertz, which is definitely going to make it a lot faster than any of the vintage machines. So among those, the BBC Micro is leading the pack, and that has a 2 megahertz 6502, which is definitely going to make it a lot zippier than the others, even just by a hair faster than the Amstrad CPC, which it just takes a little bit longer, 12.9, and it has a 2 megahertz Z80. And so that makes it a bit faster than the 3.5 hertz ZX Spectrum, and all of them are faster than that 1 megahertz Commodore 64. But what about the Nintendo? Of course, the big advertising campaign is now you're playing with power, and what it had was not a lot of memory. It's just 2 kilobytes of RAM, but of course it is a ROM-based system. And you could make these ROMs up to like 16K, which was, pretty huge back then. And with some of the different memory management units that could be embedded in those cartridges, you could get even bigger. So you had some of these ROMs were 256K or more, so fairly substantial games. Now, the graphics, on the other hand, were not necessarily that much better than some of the more popular 8-bit computers, like the Commodore 64. It definitely has some very specific limitations, not a ton of resolution, especially compared to the Commodore 64, and each of these tiles within it can only have these 4 color palettes. They are strictly 2 bits per pixel for everything in there, but it has the built-in scrolling, and I think what really sets the NES apart from the game systems that came before was the ability to do all these sprites. It had 64 different sprites, and it could reuse these tile patterns for the background or have separate tiles specifically for the sprites, and you could flip the sprites and assign Z-depth priority, all these things that really allowed the NES to come very close to being able to replicate arcade games from the early 80s. Now, as the NES, of course, went on in its life, and it's a very long life, it was starting to see the arcade slip away from it, but it was really good at doing those early arcade games. Let's take a little closer look now at the name table, because what we're going to do is we want to plot on this background a bunch of these pixels. We want to do a 32 by 22 grid of different colors, and we want to have 15 different colors. But that's not necessarily going to be possible. Let's take a look at why that is. So for each of these name tables, you can see here they have these different patterns. So there's 32 by 30. And so you've got each of these patterns has an 8-bit index. So you go through 32 bytes at a time for each row of these pattern tile indices, going all the way through 30 rows. And then after that 30th row, then you have the palette information. And you'll see here that it doesn't seem to quite take up as much memory as you'd hope. And we're going to take a look at how that's really going to affect things. So first, though, a little bit about how these patterns and palettes work. So a pattern, of course, it's just a tile, and it's an 8 by 8 tile, and it's 2 bits per pixel. So you can see here this example tile. It takes advantage of 4 different colors. So you can have each pixel having 2 bits means that each pixel will have a color value between 0 and 3. Also, each tile will have a palette value, which is also 2 bits. So you have 4 different palettes. And those are also numbered 0 through 3. But unlike some other systems like the Commodore X16 or even the ZX Spectrum, the palettes that you can use for these attributes are not self-contained. Basically, whatever the 0 color is for palette 0 is the background color for all the palettes. So really, each of these palettes are only 3 unique colors and then the background color. And as we can see here, when we try to render this tile in these different palettes, we're going to have that same background color just replicated for each of them. But then we can see that we can sort of have different usage or just different looks for these tiles depending on where they are on the screen. And even if they're used as sprites, there are additional palettes. You have 4 more palettes that you can use just for sprites. But in our case, we don't really care about that. So let's now take a look at specifically why this is not going to look like any of the other systems that we've had in this challenge. So looking here, ideally we would want to have solid colors for each of these tiles, each of these patterns just being a solid color, all colors 0, 1, 2, or 3, and then be able to have each of those tiles have a specific palette, so we have access at least to these 13 different colors. And so it doesn't quite get us up to 15. So like the 15 unique colors that we have the ZX Spectrum, we may have to like sort of dial that down a bit. But that's not ideal. But then furthermore, we can't even really do this because as you'll notice with the addressing, we only have one address for all 16 of these tiles in the attribute table, whereas the name table, we have new addressing for each row. In fact, we go up by 20 hex or 32 for each of these rows, which we can see here for the rows of the name. So this is assuming here these are the first 4 columns, sort of this upper corner of 16, upper left corner of these 16 tiles. And so yeah, the addressing doesn't work out. So we don't have individual attributes for each character. What we have are attributes for groups of 4 characters. So row 0 and 1 and columns 0 and 1 have all 4 of these have to have the same palette. So here, instead of having like palette 0 for the top ones and palette 1 for the bottom ones, it's not going to work. So if we were to have, say, for these 4, we'll have palette 0, for these 4, palette 1, these 4, palette 2, and these 4, palette 3. So we're not changing the palette on a lot of them, but you'll see the colors do shift so that now we can see all 4 of these palette 0, all 4 of these palette 1, and so we can't really within these different tiles set whatever color we want. We're stuck with just 4 solid colors, and one of them has to be black. So that's not going to work. So how are we going to do this? because we don't want to just have a 4-color plot. We had to do that with some of the other systems, and the results weren't ideal. And the NES, it was, the games that you came for it were graphically superior to most of the other 8-bit games. So one way we can do that, of course, is with dithering. And so now if we can just use one palette for all of the tiles, we can have different patterns. They're not solid colors, but they're these different dithering patterns, and so we can get 15 unique patterns to represent all of the different iteration counts for the algorithm. And here, these are going to be tiles that are numbered 0 through 14 for those index values. And if it's just 0 iterations, we will have index 1 and so forth, all the way up through 14, or rather 13 iterations, rather iteration count. And then if it's that 14 or more, we'll go to black. So we're going to need to take that count and sort of add 1 to it to get the index, unless it gets to that maximum value, and then we'll set it back to 0 to go black. And the reason why we didn't just make black at index 14 is because you generally want to have all black for that first tile, because just by writing zeros to the name table, we would want that to mean just background. And it just works out a lot better that way. Let's look at the code. Now, here we see things look a little different up at the top. Here it's including a bunch of special includes. Now, if you saw my Hello NES video, and that will be linked here at the end, and you will see I had these different include files set up for all the different register addresses that are in there, and also had sort of a header value, and then a special file to determine the character ROM. So now to get those dithered characters that we saw before, of course, we're over here, this nestchar.asm. First tile is all zeros. And you can see here you have to do sort of the low bit of the bitmap, and then the high bit for each pixel of the bitmap. You don't just have the 2 contiguous bits for each pixel like you do in, say, the Commander X16. And then here we can see color 1. Have solid color 1 means these 8 bytes that are all 1s, and then 8 bytes that are all 0s, and that'll give us 1, and so forth. And then we can see, as we go down, all these different dithering patterns to go back and forth between different colors. So here, like going back and forth between colors 1 and 2, or doing these 3-way of 0, 1, and 2, 0, 2, and 3, and eventually index 14 is going to be all 4 colors of the palette in a sort of diagonal sequence. And then from there, the rest of the characters are the bog standard character set that most NES games have. And in fact, it comes with CC65, which I'll be using to build this. So going back here to the code, once the actual code segment starts, this is where the main program ROM is going to start, and where, when you turn on the NES, it's going to start executing at this address. So we want to do a jump start for that to get to where our actual code is going to be. And then we want to have some other stuff ahead of that, including our Mandelbrot Set library. And we're just using the standard code that we've been using for all the other 6502 machines. The only difference is that I've modified this, added some more conditional features here. So now if it's NES, what I will do is instead of using the RAM in line with the code, well, we don't have RAM. Our code is all in a ROM. So I need to relocate all of our variables to the RAM segment. So I give them explicit addresses, and just to give the NES a little upper hand, I put them on the 0 page. So it's going to be that much faster. But we just really need to do that for the NES. And then we gotta just do a few things like have some more variables in there, like the plot address, which is going to be the address of VRAM, where we're going to be writing these new tile indices. And we have this NMI counter. So the NMI is what gets triggered for every VBlank, the start of every VBlank, where we have to do all of our graphics processing. Because if we don't do that, things go all wackadoo with the NES. And so we're going to just some basic window dressing. I'm not going to get too deep into here, but just to show some of the things that we have to do for an NES program, we have a couple of macros here. So initially we don't have NMI set up, so we're just going to check this bit for PPU status. And so we're just checking that the high bit for that to wait for the VBlank to happen. This other macro is once we have the NMI set, we're just waiting for this NMI counter to change. So it lets us know that a new NMI has happened, and thus a new VBlank happened. But this is a better thing to do. It doesn't create too much sort of interrupt activity, these events taking up the bus on the NES. So now, once we start, we actually want to disable those maskable interrupts. So the IRQ is going to be out there. So we're doing both SEI and setting up the APU, which is going to stop the sound IRQs from happening, because we don't care about sound here. And then setting some default values, setting all of these controls to 0. And then we wait for the VBlank, and so we're in a nice steady state. We clear out all of our RAM, and you can see here it's just doing all these, and this code is in that Hello NES, and you can take a look at that. I go into more detail of how that works. And then I want to set up my palette. So I've got my background color is going to be the first address I put in there, and then you just in consecutive writes to the data register, it will just keep incrementing that address every time you write to it. So each color is identified by a single byte. There's a limited number of colors that are available for the NES. So each color descriptor is just a single byte. So here I'm saying just red, green, and blue for those colors after the black background. And then I want to make all of name table A attributes use palette 0. And so each name table, or rather the attribute table, so the name table is going to have 32 by 30 different pattern indexes in it. But it's only going to have those 64 different indices or not really indices, but attribute values in the attribute table. And within that value is the palette. So I just set the whole attribute to 0. That just makes it simpler. And so now we're going to have palette 0 for everything. And we go ahead and write all that. And then we can enable the display because we've got all of that stuff set up, and we can get the NMI happening, which we want to sort of read from the status register to make sure that we're in a happy state. And then we, in that control register, we go ahead and say, let's do these NMIs. And then we're ready to get our plot started. So what we first want to do is set up this variable called plot address to be the very first address in name table A. So it's going to be that upper left corner. And we initialize our X and Y like we do in all these. and we call our man get. And it works the same as it did for all the others. So NA will be that count. And so we want to add 1 to it and see if we're at 15. If we're not, we go ahead and just use that value. But if it is 15, we set it back down to 0 so that it's black. So we get a nice black interior in our plot. And then we have to wait for the next V blank before we go ahead and plot that new pattern code into the name table. And so then when we do that, we go ahead and set the address with the current plot address. And then, of course, here we also kept that that value on the stack, and now we store it. So we have that that code in the name table. And now we also need to make sure that we've reset the scroll position, because every time we mess with the memory, this VRAM memory, it can cause the scroll position to go wacky. So we just make sure and say, yep, we want both the X and Y scrolls to be 0, so we're not just flying off the handle. And then we go ahead and increment our plot address. And then we are doing the rest of the loop here, where we're making sure that X is going up to the width, coming back around, and then going for the height number of rows, and we keep incrementing Y till we get to the final height. And you notice I don't have to do any sort of filling in, because just like with the ZX Spectrum, we have exactly 32 different columns in the name table, so that after the 32nd column, it just wraps right around to the next line for us. So it actually makes it pretty easy here for the NES. And then once we've finally broken out of the main loop of the plot, we go into a new loop where it just waits for each V blank to happen and keeps going ad infinitum. And then our NMI handler is real simple. It just increments that counter so that our wait NMI macro will work, and then returns from the interrupt, and that's it. We set up our interrupt vectors here at the end of memory, so that our NMI routine here actually ends up at address FFFA, and we're good to go. That's all the code that we need. So now in Messen here is a nice open source emulator for the NES, and it has some nice debug capabilities. Like, I can take a look at that PPU, and we can see here, you can see the little window going from between these different name tables. So you get a little sort of background. We can see all the different characters, and you can see they're getting changed at different points, but there's Mario. So it's neat. You can really look behind the scenes of these different games and see how they work. But now what we want to do is get our Mandelbrot set up and running, and here it is. So you can see it's going pretty fast. But how fast is it? I'm going to need to get my stopwatch here for the second run, but it looks pretty good. And with this dithering, we get a good chance to see all of the different iteration values through there. All 15 different values are nice and clear, nicely differentiated. I am going to now do it with the stopwatch. And if I do just a reload ROM, that's going to be the quickest way for me to do it. So let's go. All right. We're going. We're still going. We're going through the big heavy middle. Now coming back down the pike. And come on, NES, and done. 16.2 seconds. Not too bad. So that's how powerful it is. Let's take a look at how it compares now to the other systems. So there it is. It is in a respectable 5th place. It is slower than the Spectrum, but it's faster than the Commodore 64. Even if the color isn't as nice on there, we had to resort to those dithered tiles. but it is faster than a Commodore 64. So there it is. That's what we got here for this latest entrant into the 8-bit Battle Royale. And we're going to keep going too, because I don't like the Commander X16 sitting up there by itself. There are other modern 8-bit computers that are just waiting to eat its lunch. So we're going to take a look at some of those in the next installment of this video. But until then, if you want to see that video before anybody else, there's one way to do it. Come join us on Patreon right here, and like these folks can see all of those videos as soon as they're ready. I upload them and they get to see them ad-free, and then also provide a lot of feedback for the channel and really be a part of the creation process here. So I thank you. If you aren't already subscribed, please subscribe to my channel. I'm going to have a lot more fun stuff like this coming up. And make sure to give a like and a comment. And you can even give a dislike, but YouTube's not going to tell me how many dislikes I'm getting unless I really dig for it. So if you don't like the fact that I'm using emulators, well, just know that nobody else is going to see how much you dislike unless you make a big fuss in the comments. All right. Anyway, I hope to see you again very soon. Until then, bye-bye.